Digital communication relies on coordinate geometry. To transmit information, a system maps raw data streams into discrete states, points plotted within a predefined signal space. Consider these two modulation schemes, 16 QAM and 16 PSK. Both configurations carry identical data capacity, encoding 4 bits of information into every transmitted symbol. Both geometries must also survive the same environmental hazard, additive white Gaussian noise, which continuously distorts the signal's position as it travels. Despite holding identical data capacities and facing the same channel conditions, these two configurations yield vastly different real-world error rates. This chart plots symbol error rate on a logarithmic scale against average signal-to-noise ratio per bit. This solid line represents the 16 QAM performance curve. Compare it to 16 PSK. At identical signal power levels, the circular configuration yields a significantly higher frequency of errors. Understanding the origin of this performance gap requires deconstructing the mathematics of optimal receiver detection. We will first attempt an exact probability mapping using multivariate integration before proving a highly efficient closed-form shortcut. Translating abstract probability into strict geometric boundaries provides the predictive framework necessary to choose the right modulation scheme for a specific channel. Identifying the origin point of a signal is complicated by noise, a random variable with infinite tails that can push a signal to any point on the coordinate plane. To minimize errors, the map detector calculates the probability a specific symbol was sent. Assuming equal frequency, we discard prior probabilities and the denominator, isolating the Gaussian density function. Maximizing this is mathematically equivalent to finding the minimum squared Euclidean distance. This reduced state is defined as the maximum likelihood detection rule. Geometrically, the receiver simply snaps the incoming noisy signal to the absolute nearest valid symbol in the constellation. This nearest neighbor logic effectively partitions the entire coordinate plane into distinct decision territories for each symbol. While executing the nearest neighbor rule is computationally cheap, calculating the statistical probability of an error occurring across the entire plane remains difficult. Finding the closest target point requires basic distance math, but proving the exact failure rate of that logic requires mapping probability across infinity. Let's attempt an exact calculation of the overall error rate from first principles, using the 16 PSK constellation. The decision boundary for a single 16 PSK symbol is an infinite triangular wedge, projecting outward from the origin point. The exact probability of a correct decision requires integrating the joint noise probability density function exclusively over the volume captured within this triangular wedge. This introduces a geometric mismatch. Gaussian noise is defined on Cartesian axes, but our decision region is strictly radial. We must apply a Jacobian transformation to serve as a mathematical bridge, shifting the Cartesian noise data into polar coordinates. This substitution results in an expression where the complementary error function is embedded inside a second, unresolved integral operating over the angle theta. This integral is structurally impossible to solve in a closed analytical form. Because we cannot solve it algebraically, we are forced to use numerical integration, calculating tiny iterative slices to approximate the area. To plot a full performance curve, this heavy numerical process must be repeated for every single possible signal-to-noise ratio. While exact multivariate integration provides a precise theoretical answer, the computational intensity makes it a bottleneck for practical system analysis. We can avoid this complexity by looking at the geometry of 16 QAM and applying an alternative analytical approach. This is the union bound. It assumes error rates are dictated by a signal crossing the threshold towards its immediate adjacent neighbors. The critical threshold is the minimum Euclidean distance separating any symbol from its nearest neighbors, a value denoted as d. Unlike the uniform 16 PSK ring, the 16 QAM grid is non-uniform. Symbols have different neighbor counts. The 4 innermost points are the most vulnerable, surrounded by 4 nearest neighbors at distance d. The 8 outer points face only 3, and the 4 corner points are most protected, with only 2. To find the average error rate, we aggregate the constellation by weighting the specific neighbor counts of each group. This weighting collapses the problem into a single, clean equation. We've transformed an intractable calculus problem into a fast arithmetic shortcut. The union bound provides a highly accurate approximation of system performance, driven entirely by spatial geometry. When we compare these theoretical union bound curves against our simulation data, the accuracy is immediately apparent. In low SNR regions, the bound is slightly loose. High noise occasionally throws signals past immediate neighbors, causing the shortcut to slightly overcount total errors. But at higher SNRs, the bound tightens. The statistical likelihood of jumping past a nearest neighbor vanishes, and the approximation locks onto the exact plot. This convergence provides the mathematical explanation for why 16 QAM outperforms 16 PSK. Remember that both schemes are constrained by the same average transmit power allowance. 16 QAM's square layout inherently maximizes the minimum distance d between its data points for that given power level. While 16 QAM has more nearest neighbors on average, the union bound shows this multiplier is only a minor linear penalty. 16 PSK, by contrast, forces all points onto a single ring, which severely shrinks the distance d between symbols. Because distance d is part of an exponential term in the error function, this smaller distance results in a much higher rate of signal failure. Against the constant presence of Gaussian noise, the strategy of maximizing geometric distance and validating it with the union bound is why 16 QAM remains the standard for high-speed data transmission.